Imagine, if you will, the universe as an infant, just 380,000 years old, still glowing from the Big Bang's fiery birth. That glow, that ancient whisper, is what we call the cosmic microwave background, the universe's very first baby picture, plastered across the entire sky. It should be perfectly smooth, a uniform cosmic canvas, save for tiny predictable ripples, the seeds of future galaxies. But then we saw it, a vast, impossibly cold void, a gaping bruise smeared across that pristine cosmic canvas, stretching billions of light years. It's a place where the universe simply forgot to heat up, an emptiness so profound, it defies every law, every model, every single assumption we've ever made about reality. This isn't just a cold spot, it's a cosmic scream. But what could leave such a terrifying mark on the very face of creation? They called it the cosmic microwave background, a faint echo, the afterglow of the Big Bang itself. In 2004, when the WMAP satellite finally mapped this ancient light with unprecedented precision, the universe offered us its baby picture. And it was flawed. A vast supercooled patch, spanning roughly 1 billion light years across the constellation Eridanus, glowed with a temperature far, far colder than it had any right to be. We're talking about a temperature drop of a mere 70 microkelvins, tiny to us, but on a cosmic scale, it screamed anomaly. This wasn't just a slight dip, it was a statistical impossibility. Picture an exquisitely woven tapestry, perfectly uniform in its thread count. Now imagine a patch, a full 10% of its surface, where the threads are inexplicably sparse, almost threadbare. The cold spot was like that. Our best cosmological models, born from the very Big Bang Theory, predicted temperature fluctuations across the CMB. Yes, but nothing this extreme, nothing this stark. The odds of such an immense cold spot appearing randomly, purely by chance, were less than 1 in 100,000. Some brave souls even dared to suggest a 1 in a million chance. To a scientist, those are lottery numbers for cosmic weirdness. The initial reaction from the high priests of cosmology: dismissal. A statistical fluke, they declared. An observational error. Nothing to see here, move along. It was the scientific equivalent of shrugging off a gaping wound. The universe, they insisted, must be uniform on these grand scales. The Big Bang model, our sacred text, demanded it. To accept the cold spot as a genuine feature meant questioning the very foundations of our understanding. It meant admitting the universe was not just stranger than we imagined, but stranger than we could imagine. But the data, relentless and unforgiving, persisted. That impossible bruise refused to fade. It hung there, a chilling testament to a secret the cosmos was desperately trying to tell us. The scientific community, initially resistant, couldn't ignore the persistent chill. The cold spot gnawed at them, a dissonant note in the cosmic symphony. If it wasn't a statistical fluke, then what was it? The hunt began. This wasn't just idle curiosity. It was a desperate scramble to preserve our cosmological sanity. If the cold spot was real, it demanded a physical explanation, a cosmic culprit. The most plausible, least radical explanation quickly emerged: a supervoid. Imagine a region of space so utterly gargantuan, so mind-bogglingly vast, that it's almost entirely devoid of galaxies, gas, and even dark matter. A cosmic desert stretching for hundreds of millions, even billions of light years. If photons from the cosmic microwave background had to journey through such a colossal emptiness, they would lose energy. As light climbs out of a shallow gravitational well, it loses a tiny bit of energy, a phenomenon known as the integrated Sachs-Wolf effect. In a supervoid, where gravity is significantly weaker due to the absence of matter, photons would experience a net energy loss, arriving at our detectors slightly cooler. It was a brilliant hypothesis, elegant in its simplicity. So, the telescopes turned. In 2015, a team of astronomers, using data from the Vista telescope, announced a breakthrough. They had indeed found a supervoid in the exact direction of the cold spot. It was colossal, spanning approximately 1.8 billion light years across the constellation Eridanus, the largest single structure ever identified in the universe. It was, by all accounts, a cosmic vacuum. A collective sigh of relief echoed through the halls of astrophysics. The mystery was solved. The cold spot was merely the shadow of this titanic emptiness. Our standard cosmological model, the one that said the universe should be uniform, remained largely intact. We had found our cosmic culprit, but the relief was fleeting. As the data poured in, as more precise measurements were made, a chilling discrepancy emerged. The Eridanus supervoid, while undeniably massive, simply wasn't empty enough. It contained an average matter density of about 30% less than the rest of the universe. That's a significant deficit, yes, but according to our calculations, a void of that size and that level of emptiness could only account for about 10% of the observed temperature drop. It was like finding a small puddle and expecting it to explain a massive flood. The cold spot was still too cold. The supervoid theory had promised to be the elegant solution, the neat bow on a perplexing package. Instead, it only deepened the enigma. It was a piece of the puzzle, certainly, but not the whole picture. The universe, it seemed, was still holding back its darkest secret. The Eridanus supervoid was real, and it did contribute to the cold spot. But it couldn't explain its profound, impossible chill. It meant that something else, something far stranger, far more radical, had to be at play. The quest for the true origin of the universe's most inexplicable bruise was far from over. If this cosmic detective story, peeling back layers of universal mystery, ignites your curiosity, then smash that like button and subscribe for more deep dives into the universe's most mind-bending secrets. Your support helps us chase these cosmic whispers across the void. If a mere supervoid couldn't explain the cold spot's impossible chill, then what could it? This was the question that haunted cosmologists, pushing them to the ragged edge of known physics. The statistical anomaly was too stark, the temperature drop too profound. It demanded an explanation that transcended our current understanding of cosmic structure. And that's when the truly audacious ideas began to emerge, whispered at first, then shouted from the rooftops of scientific conferences. The most radical, the most mind-bending hypothesis of all posited a collision, not between galaxies, not between black holes, but between universes. Imagine our universe, a vast, expanding bubble in a boundless ocean. Now imagine other bubbles, other universes, floating nearby. What if, in the chaotic infancy of our cosmos, our nascent universe brushed against or even collided with another, a cosmic fender bender, on a scale that defies comprehension? This theory, known as the bubble universe, or multiverse collision hypothesis, stems from the concept of eternal inflation. This isn't just a speculative sci-fi trope, it's a serious extension of inflationary cosmology, the very theory that explains how our universe grew from a quantum speck to cosmic immensity in a blink of an eye. Eternal inflation suggests that the process of inflation, once it starts, never truly stops everywhere. Instead, it perpetually creates new bubble universes, each one an independent cosmos with its own set of physical laws, its own dimensions, its own fate. Our universe, then, is just one bubble in an infinitely frothing cosmic champagne. Now picture two such bubbles expanding rapidly. If they were to collide, even a glancing blow, the impact would leave a catastrophic imprint. The bruise would manifest as a massive, localized disruption in the fabric of space-time itself. The collision would create a region of significantly lower energy density, a colossal dent in the early universe's energy field. And what would such a dent look like when imprinted on the cosmic microwave background? Precisely a cold spot. Photons traveling through this collision-scarred region, this cosmic bruise, would experience a much deeper gravitational well than usual. They would lose far more energy as they climbed out, arriving at Earth with a vastly reduced temperature. This enhanced energy loss could finally account for the cold spot's extreme, inexplicable chill, a temperature drop far beyond what a simple supervoid could produce. It would be a direct echo of an ancient, unimaginably violent event. The implications are staggering. If the cold spot is indeed a bruise from a multiverse collision, it means our universe is not alone. It means the very concept of universe as a singular entity is shattered. We would be living within a cosmic archipelago, a boundless ocean teeming with other realities. The cold spot, then, isn't just an anomaly. It's a window, a direct observational portal into the vast, churning multiverse. It's the most profound piece of circumstantial evidence we've ever found that suggests other realities exist, pressing in on our own. Of course, proving such an audacious claim is a monumental task. The precise shape of the cold spot, its specific temperature profile, and the way it interacts with surrounding cosmic structures all hold subtle clues. Scientists are meticulously analyzing every pixel of CMB data, searching for the telltale textures or asymmetries that a collision might leave behind. It's a cosmic forensics investigation where the crime scene is the entire early universe and the only evidence is a billion light-year-wide bruise. The stakes couldn't be higher. Nothing less than the fundamental nature of reality itself hangs in the balance. Is the cold spot merely an empty corner of our universe? Or is it a direct, chilling whisper from another? The audacious multiverse bruise theory, while exhilarating, is far from proven. It stands as the most tantalizing, yet most challenging explanation for the cold spot's impossible chill. The scientific community, now fully engaged, has transformed this cosmic anomaly into a high-stakes detective case, employing every cutting-edge tool at their disposal to either confirm the multiverse or reaffirm our current singular cosmic understanding. The investigation is relentless, driven by the profound implications of either outcome. One major front in this cosmic forensics battle involves advanced statistical analysis of the cosmic microwave background data itself. Beyond just temperature, scientists are scrutinizing subtle patterns in the CMB's polarization, the orientation of light waves, and searching for non-Gaussianities. Standard cosmological models, which don't account for inter-universe collisions, predict that the CMB fluctuations should follow a specific Gaussian or bell curve distribution. A collision, however, would likely introduce distinct non-Gaussian signatures, creating hot or cold spots with unusual shapes or sharp edges. While initial searches for these specific patterns haven't yielded definitive proof, the data is constantly being refined, and new, more sophisticated algorithms are being developed to tease out these elusive signals from the cosmic noise. It's like searching for a specific fingerprint on a canvas painted billions of years ago. Another crucial line of inquiry focuses on mapping the three-dimensional structure of the Eridanus supervoid with unprecedented precision. The discrepancy between the supervoid's observed emptiness and the cold spot's extreme temperature drop is the critical weak point for the single universe explanation. New surveys, like the Dark Energy Spectroscopic Instrument, DCEI, and the upcoming Euclid Space Telescope, are designed to create vast 3D maps of galaxies, allowing astronomers to trace the true distribution of matter and emptiness across billions of light years. If these surveys reveal that the supervoid is even emptier than currently estimated, or if they uncover additional, smaller voids aligned in a specific way, it could strengthen the supervoid hypothesis, perhaps even allowing it to account for the full temperature anomaly. Conversely, if the emptiness remains insufficient, it pushes the needle further towards exotic physics or the multiverse. Theoretical physicists are also working overtime, developing increasingly complex simulations of both cosmic void evolution and multiverse collisions. Can a standard cosmic void, under extreme but plausible initial conditions, really create such a deep cold spot? Can various multiverse collision scenarios generate precisely the observed temperature profile, spatial extent, and statistical properties of the cold spot? These simulations, running on the world's most powerful supercomputers, are testing the boundaries of our models, trying to find a theoretical pathway that leads directly to the Eridanus cold spot. They are exploring exotic forms of dark energy that might behave differently in voids, or even alternative theories of gravity that could amplify the cold spot's effect without resorting to other universes. The stakes are astronomically high. If the cold spot is a statistical fluke, then our current cosmological model, the Lambda CDM model, stands robust, a testament to decades of scientific triumph. It means the universe, while vast and mysterious, largely conforms to our expectations on the largest scales. But if the cold spot turns out to be a genuine signature of a multiverse collision, then everything changes. It would mean we are not alone in the truest sense of the word. It would open up an entirely new frontier of cosmic exploration, forcing us to redefine our place in a potentially infinite tapestry of realities. It would provide the first empirical, albeit indirect evidence, that our universe is just one bubble among countless others, each with its own unique laws and characteristics. This cosmic enigma forces us to confront the limits of our knowledge, to push beyond the comfortable boundaries of what we thought was possible. The cold spot is more than just a cold patch. It's a cosmic challenge, a tantalizing hint that the universe is far wilder, far more intricate, and potentially far more populated than we ever dared to dream. The investigation continues, a testament to humanity's insatiable drive to uncover the universe's deepest, most unsettling truths. The Eridanus cold spot, that colossal bruise on the universe's baby picture, remains one of the most profound enigmas of our time. It is a testament to the fact that even in the vast, seemingly empty expanse of space, the cosmos can scream secrets too chilling, too radical for our current understanding. Whether it's the shadow of an impossibly deep void or the ghost of a collision with an alien reality, the cold spot forces us to confront the true strangeness of existence. It reminds us that our universe, for all its apparent order, harbors anomalies that defy our most cherished models, pushing the boundaries of physics and sparking the most audacious theories imaginable. This cosmic riddle, born from the very first light, is not just a scientific problem, it's a philosophical challenge. It asks us if we are truly alone or merely one bubble among an infinite froth of realities. It forces us to ponder the very nature of creation, the limits of space, and the possibility of other universes lurking just beyond our cosmic horizon. The cold spot is a beacon of cosmic mystery, a chilling whisper from the quantum foam of creation. It stands as a monumental reminder that the universe, in its boundless complexity, will always hold secrets that ignite our imagination and compel us to journey ever deeper into the unknown. Tell me what you liked or disliked about this video. What do you think could be changed to make it better? I read every comment and will respond to every suggestion.